Good afternoon. This is the first asynchronous material for Statistics and Statistical Computing 2, EDF 803. And what we're going to do in this period is very briefly review what was in Stats 1 in terms of inferential tests. So when Stats 1 introduces the inferential tests, that's tests of a null hypothesis, essentially that there is no effect or no difference between a statistic based on a sample and a population parameter. You start with z-tests, and z-tests are the comparison of a mean to a population mean. And because they're a comparison to a population mean, to perform a z-test, you need to know the population mean and the population standard deviation to perform a z-test. So it would be, for instance, when you have a sample of individuals who have taken an intelligence test, you know that the population mean for an intelligence test is 100. Say you're talking about the WISC, and the standard deviation is 15. So you have your sample has a mean and a standard deviation, and you can construct the exact probability of that sample's characteristics in the unit normal compared to the unit normal distribution and find out where the probability or how probable your sample mean is based on the normal distribution characteristics. And then you can compare that to your standard for probability or your alpha level. So the z-test is only used when you have population parameters, and in social science research, it is rarely used. In educational research, it's rarely used because we rarely are interested in measures that have known population parameters. The one sample t-test is very similar to the z-test in that it tests a sample statistic against a mean that is known and does not require a second sample to establish that mean. It is, though, the case that the mean that it's tested against, that you do not know the population standard deviation. So this would be a case, for instance, when you have a target mean, what I call a target mean. So you know the average age of New York City school teachers. You have a sample, the sample as a mean and standard deviation. You do not know the standard deviation of the population of New York City school teachers. So you can't use the Z because you don't have the full information on the distribution. In the t-test, one sample t-test, you compare your single sample to the target mean or the population mean, if you know the population mean. But rather than use the population standard deviation, you use the standard error of the mean, which is the standard deviation divided by the square root of n. And your difference between your mean and your target mean divided by that term gives you a t-statistic. And the t-statistic is part of a family of distributions, and you have to look up in the tables what value represents the probability that corresponds to your alpha level, and you test against that value. But it's very similar in that in terms of a design, you only have one sample. And that's the basis for all of your inferences is the comparison of this one sample to some expected value. This again is somewhat unusual. It's not a very strong research design. So we don't see it very often in the literature, and we would prefer not to use it in our own research because it is just not a particularly strong research design. There's no comparison group is the main issue with it. You're using some kind of static comparison group taken from the census or public records or something like that. So the third test you would have done is the two independent samples t-test, in which case, obviously from the name, you've gathered two samples of data and you're going to compare their means. And in this case, you need the full raw data, or at least you need the sample means and standard deviations. You test the difference in those means divided by the standard error of the means, and that gives you what we call the obtained t-statistic, and you compare that to what we call the critical t-statistic that corresponds to the probability of obtaining that t-statistic in given the degrees of freedom, which like locates you in the t-family of distributions. And basically it's a comparison between two sample means. Those samples have to be independent. They can't have any overlapping cases. So there can't be anybody who's in one sample and also in another sample. They shouldn't be, for instance, relatives. They're not paired. So it isn't one sample has sibling 1 and the other one has sibling 2, and so on. So for the case where you have what are called dependent samples, which might be pairs of matched people, it might be parents matched with their children's or paired with their children's, it might even be the same people measured twice, which is very common in research, which is like a pre and a post score. And those are called paired or dependent or related sample t-tests. As I said, it's very common. It needs a different test because it violates one of the assumptions of the t-test, which is that the samples don't overlap. They're not correlated, they're not related. And so it has a different test. The test simplifies actually to a one sample t-test of the differences between each case. So a one sample t-test of difference scores. And you should have covered all of those in the first semester. And the logic of them is basically a difference between means where you have one or two samples only. So the last thing you probably covered in Stats 1, and where we're really going to start in Stats 2, is the one-way ANOVA. ANOVA stands for Analysis of Variance. And ANOVA is appropriate when you have more than two samples whose means you want to compare. And so you have one Y variable, that's your dependent variable, and one X. A one-way ANOVA is when you have one independent variable, but it has more than two levels. There's more than two samples. So rather than treatment and control, you have treatment A, treatment B, and control. So that's all your treatment condition independent variable, but rather than one group or two groups, you have three groups. So a t-test only does what we call a pairwise comparison at most. It compares one mean to another. So it can't compare among three means. So that's the case where you're going to use an ANOVA. And what I'm going to cover in this is the when ANOVA is appropriate, how you set up the hypotheses, the significance level, the critical value, the assumptions, obtained statistic, null hypothesis, significance test, and effect size. I'm going to go over these very briefly because we will go over them in the first class in more detail. So first of all, the ANOVA is what's called a between subjects test. That means that it's a comparison of means for different groups. It's not a within subjects test, which would be when you have one group of people who are measured more than once. So that's a within subjects design. It's, the dependent samples t-test is a special form of it. And that's not what a one-way ANOVA is. A one-way ANOVA is when you have two or more separate groups. It tests against what's known as the F distribution, which we'll look at in a minute. And the ANOVA test is one factor. That means that you have one independent variable, one X variable, and it has more than two levels. The dependent variable must be continuous. So it might be intelligence, it might be motivation, it might be intention to leave a profession, but it is not like a binary variable. And the factor is obviously categorical because it's some kind of group membership. So that slide shows you a summary of those characteristics. Setting up the hypotheses. What we're going to cover in the first class is what's known as the omnibus test, which is kind of the initial test in an ANOVA. And in fact, it can be either a starting point or an ending point, depending on the kinds of questions you want to answer. But the omnibus test has a null hypothesis, that's H sub O, which can be written in a variety of ways. It can actually, it's not that unusual to see someone write a null hypothesis in ANOVA as a written statement, which is that there's no difference among the means, or the mean for the first group, mu for the first group. In a hypothesis language, you use the population parameter notation, is equal to mu for the second group, is equal to the mu for the third group, on and on through the mu for the jth group. J means represents the maximum numbered group. And the alternative hypothesis, which is the one generally speaking you would like to uphold or find for, is that there's at least one difference among the means, or the mean for one group is not equal to the mean for some other group. Let me see if I want to say anything about this. Oh, just usually in a APA type write-up on results, you do not state the hypotheses in this formal way. You might say we're going to test the null hypothesis that there's no difference among the means, or we're going to test the hypothesis that one mean is different from another, but you're not going to write them out in this H sub O, H sub 1 format. So then after we set up our hypotheses, you have to know what your hypotheses are. You have to be able to articulate them. And I will ask you often to write them out, but they're not usually written in a professional write-up. Then you establish your level of significance. You probably remember this. Your level of significance uses the notation alpha. It is an a priori value, so you have to set it up front, basically when you're stating your hypotheses. And there's some conventions in the social sciences. You will normally see an a priori alpha of 0.05 or 0.01, less commonly 0.001. And what that means, say an alpha of 0.05, means that if your obtained statistic is less than 95% likely to be found under the null distribution, so if it's beyond the bounds of the 95th percentile, then alpha equals 0.05 or 1 minus 0.95, and you are going to say that that finding of your obtained statistic, which is beyond the 95th percentile, is not likely due to chance, not likely due to random sampling under the random sampling error or random sampling variability under the null hypothesis distribution. Now, if it's not likely due to chance, you're going to claim that it's likely due to your independent variable and a non-chance effect among the levels of your independent variable. How well supported that finding is based on your research design. So your interpretation of the finding that something is statistically significant or is at the level of your alpha or less probable than that is that your finding is not likely due to chance. And what you say is you reject the null or you accept the alternative hypothesis that your finding is not likely due to chance. You cannot go straight to causation unless supported by your research design. So once you have your alpha level, then you can find a critical value for a test. In SPSS, your output will give you the exact probability of your finding, which you then compare to your alpha. But if you're not using a statistical package, then you're probably going to set a critical value, which your obtained statistic must exceed. And the critical value is based on the distribution that you, that is the comparison distribution for the test of the omnibus null hypothesis. This is not the T distribution. This is the F distribution. The F, again, like the T, is a family of distributions. It is not shaped like the normal distribution. It is, there is no such thing, for instance, as a two-tailed F test because it's asymmetrical. It's a distribution of ratios. And as a distribution of ratios, there's a degrees of freedom term for the numerator and for the denominator. And I'll go in a minute into where that numerator degrees of freedom comes from and the denominator degrees of freedom. But the critical value is a function of both of them. And the tables for the F distribution are arranged by the intersection of 2 degrees of freedom. And the degrees of freedom are a function of the sample size and the number of groups. So we'll look at that in more detail, either in class or later in these slides. Once you have done these things, these are all a priori. You determine whether ANOVA is your right kind of test. You set up your hypotheses. You establish your level of significance. And if you're using a critical value test, you find the critical value. Now you look at your actual data and you check the assumptions of the ANOVA. So you have to be at the right level of measurement. You have to have a continuous interval or ratio level dependent variable, and you have to have a categorical independent variable. It can be categorical or ordinal. So to restate that, your independent variable can be categorical or ordinal. Your dependent variable should be interval or ratio. If you have, you can have kind of an unlimited number of categories for your independent variable, but it becomes rapidly very difficult to reject a null if you have a lot of categories. So usually we're talking about, categories of 3 through 5 maybe, unless you have a really large sample. So that has to do with the number of groups being compared. So really the number of groups on your independent variable is part of your research design, but you need a very large sample to compare a whole lot of groups. And I'm not sure why you would want to, what kind of hypothesis that would be. But if you only have two groups that you're comparing, two sample means, you can use a t-test. So generally, you're only going to use a one-way ANOVA if you have more than two t-tests. Your sample size usually should be balanced. So a balanced test isn't an assumption of ANOVA. So when it says check assumptions, it's really more like check what I sometimes call desiderata, which are things that you need or you would like to have, but they're not must-haves. And sample size is more like something you want to have, and you want to have as large as possible a sample, and you want to have balance among the groups. So you can't have any group that just has one case, because then you have no variability. And usually you want the groups to be of equal size. Always you want the groups to be of equal size. And that's because of the assumptions, particularly the last assumption listed here, which is the homogeneity of variance. So you're less likely to meet the assumption of homogeneity of variance when you have unbalanced group sizes. And the other assumptions, I think that the only ones, I'm going to skip validity of the model, we'll come back to that later. The observations have to be independent. That means that there can be no overlap, just like in a t-test, that the groups have to be separate. No one can belong to more than one group, and the members of one group shouldn't in any way be contingent on the members of another group. The assumption of normality is that the underlying distribution of the dependent variable should be normal. It's unusual for your sample to be exactly normally distributed on the dependent variable, but it should be within the realm of sampling error. You will have problems if you have an extremely skewed data set. And so you do want to check that assumption. And as I said, the homogeneity of variance assumption, which can be checked. So you mostly should look at the first two of those assumptions in your design, and the normality assumption and homogeneity of variance in the analysis. And we'll do both of those in class. Then you're going to get the statistic, and we're going to go through this in detail in class. But the F statistic is the variance between groups. That's the variance between groups. If you have multiple groups, their means vary. They do not all have the same mean, and therefore there is variance among the means. And that's called between group variance. You see the sigma squared, which is the way we're accustomed to writing variance. In ANOVA, it's common to write variance as capital MS with a lowercase to represent between group, and that stands for mean squares. It's a tradition in ANOVA to use that notation, and you will see it frequently. The denominator is variance within, which is another way of saying random error variance. So it's just the fluctuations in the sample that are not attributable to group characteristics. So they're not explained by group differences. They're considered unexplained or variance. So it's the ratio between what you can explain in the data set, the variance that is systematic between the groups, to variance that is not systematic. Now, obviously you want it, well, maybe not so obviously, and I will talk about this more in class, you want this to be greater than 1. You want there to be more differences between the groups that can be explained by group membership than unexplained variance. Once you have your obtained statistic, you're going to make your decision about the null hypothesis. If your obtained statistic is greater than your critical F, you're going to reject the null. And if it's less than or equal to your critical F, you're going to fail to reject the null. There are no one-tailed omnibus ANOVA tests. If you are looking at the exact probabilities as reported in SPSS, if the p-value for your results is less than alpha, you're going to reject the null hypothesis. And if it's greater than or equal to alpha, you're going to fail to reject the null hypothesis. Ignore this recall because there is no such thing as a one-tailed test in ANOVA. That's more of a general thing that includes t-tests. So the bottom recall for one-tailed test, you can just ignore in here. After the null hypothesis significance test decision has been made, you interpret results. Remember, you cannot say that the rejection of a null hypothesis is because the independent variable caused differences in dependent variable, unless you have a really strong research design. What you can say is that they're not likely, the differences among the groups are, the mean differences among the groups are not likely due to chance. And then if you have rejected the null, you can look at the effect size of the differences between groups. How large in magnitude are the differences in groups? And in ANOVA, that is communicated by a term called eta squared, which is the percent of variance that in the data set that is related to between groups differences. And just a quick comment on the notation that I use in one-way ANOVA. This is mostly the general notation that you will see in your textbook. Basically, I think the only thing that's unusual is the bottom point. So one-way ANOVA has only one factor. Independent variables in ANOVA are usually referred to as factors, and the factors have multiple levels or groups. So if you have a factor that's temperature, and there are 3 levels of temperature that people are assigned to, 50 degrees, 70 degrees, and 90 degrees. So this is the way it is in my offices at Hunter. I go back and forth between offices. One of them is cold, it's 50 degrees. One of them is medium, it's 70 degrees. One of them is very hot, it's 90 degrees. So if you put all the faculty in the School of Education in the 50-degree setting, you put all the faculty in the humanities in the 70-degree, this is a lousy research design, but whatever. And all the faculty somewhere else in 90 degrees, and you tested their concentration. Concentration is the dependent variable. The factor is temperature. That's your X. And the X has 3 levels or groups, 50, 70, and 90. So the factor is the X variable, and the levels or groups are the way that that X is categorized. So J represents the number of levels. So J in the case I've just described is 3. So if you have an Xij, that's a single score. That's my concentration. Right now I'm sitting in the 70-degree climate. So if I'm the first case in the data set, my value is X12, where J means I'm in the second condition, which is the 70 degrees. So X14 would mean that there are at least 4 levels of the factor, and you have the first case that represents, that belongs to the 4th level. The group means are indicated in the subscript. So X bar is a mean, and the sub 3 is which of the J levels a mean belongs to. So X bar sub 3 means the mean for group 3. The grand mean, which is the mean of all the means, or the mean of all the concentration values in the entire sample, is X bar sub dot, which is just called the grand mean. No one says subdot. X bar grand, and that's the mean of all the means. So it's used with a subscript of a dot. And for the total sample size that's collected across all the groups, so it's all the cases regardless of group membership, I use n dot. Capital N is what some people use, but that's really normally a population value, so I don't use it. I use n dot, analogous to the X bar dot. And then I represent group size with a small case n or an n sub j. So those are the notation things you're generally going to see in this class. Every once in a while I slip up on my notations and I use something that's a convention that is a little bit different than you'll probably see in the textbook. And someday I'll make a translation between all the different forms of notation that people use, but I haven't done so yet. So that's everything for this video. I hope it was a helpful refresher and will be useful to you for the first class and useful to you in the future.